you're going to just miss it. But hey, there, the recording's on. So ready? Review. Right there. Now we're down to here. You missed the first 5 minutes. All right, so what do? So if you need to find this Taylor series, okay, this x minus a to the first, to the second, to the third, that's always the same. And of course, this 2 factorial, 3 factorial, 4 factorial come from taking the derivatives. So that's always the same. So what you need to do is find the function, its derivative, its second derivative, its third derivative, and plug in the a to determine the coefficients. So once you've kind of get your head wrapped around it and you've done a bunch of these, then I think you can go a little faster. So let's see if we can do that for sine x. So I'm going to just start on a clean piece of paper. Say f of x is sine x, and then we want it at x, or a, I suppose, equals pi over 3. Okay, so I'm estimating sine x at pi over 3. I really wouldn't have to do it at pi over 3 because, as you guys found out, sine, come on, thing, there it goes. The sine function converges everywhere, right? The radius of convergence is infinity. So you can just find the Maclaurin one and stick in a pi over 3, it works fine. But for some of them, especially where the radius of convergence is only 1, if its radius of convergence is 1 and it's centered at 0, that means that the polynomial is only good from -1 to 1. Which means if you need to estimate or find a value at 2 or 5, then that approximation is not going to work, and you're going to have to use a Taylor polynomial that's centered at 5. Okay, so here we go. So you're thinking, if I want to approximate with the polynomial, then I need to find all the derivatives, and I need to stick in the pi over 3. So what I would do is I would say f of x equals sine x, and f prime of x equals the derivative of sine. Is that cosine? And then the second derivative of cosine, opposite sine. And then the third derivative of minus sine, derivative of minus cosine. And then the fourth derivative, if you want to go this far, right, fourth derivative, derivative of minus cosine is minus a minus sine, which is back to sine again. So how far do you got to go? Generally, 4 or 5 of them will be enough that you can see the pattern. Now what we have to do is stick in pi over 3. So at pi over 3, I got the sine of pi over 3. Well, pi over 3 is what, 60 degrees? So the sine will be root 3 over 2. The derivative of pi over 3, that's the cosine of pi over 3. So if I'm up root 3 over 2, I must be over a half. And maybe you'd want to draw a unit circle, okay, so that you can make sure that you're getting these values right. Maybe you'd want to just put them into your calculator to confirm that you're actually remembering the values correctly. Or maybe you just trust your memory. Live that up all you can, because eventually you might not remember things quite as easily, without coffee anyway. Stick in pi over 3, sine that's minus root 3 over 2. So the fourth derivative, am I off? Yeah, third derivative. Third derivative, minus cosine, that's minus a half. And then of course we wrap around again to the fourth derivative of pi over 3. We're back to the sine, so we're back to root 3 over 2. Okay, so this process be the same, doesn't make any difference what the function is. Take the derivative, take the derivative, take the derivative, take the derivative, plug in whatever a is, and get that part of the coefficient. And then the rest is just writing it out. So what do we say? We say sine of x is equal to, it's going to be equal wherever our polynomial converges. And we already know that this polynomial is going to converge for all real numbers, so we're good everywhere. Mostly we just write equal, even if they're not really completely equivalent. And the equal means they're equal when they're equal. So there could be some problems with the domain, right? is what we usually do. And so we kind of loosen our definition of equals up a little bit here to include, you know, it's mostly equal. But in this case, it is equal. All right, so what do we got? We've got the first coefficient, which is, it's got to agree at the value. So we say root 3 over 2 plus, and then we go whatever the next derivative is. Notice that when we did this at 0, since sine is 0 at 0, right, we only ended up with the odd terms. But here we're going to end up with lots of terms. Okay, stick in the next one. So what is it? It's 1/2, right? It's 1/2, 1 over 1 factorial, x to the first power. And then we've got what? We've got minus root 3 over 2. And then we've got a 1 over 2 factorial down here, x to the third power. Whoops, x to the second power. And then we've got a minus 1/2, 1 over 3 factorial, x to the third power. And then with this dot, 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 as long as there's a dot, 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 then these two things are going to be the same, right? In other words, this polynomial is getting closer and closer to sine as we add more terms. Of course, we would have to prove that it actually converges to sine, meaning we would have to prove that the dot, 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 okay, that we're adding is getting smaller and smaller and smaller and smaller and smaller, so that the error between these two functions is getting smaller and smaller. Now, I didn't go back and prove that, right? It's a limit proof. It's a little messy, and you can read about it, okay? It's called the remainder theorem. And what we have to prove is that the remaining terms disappear. Because if the remaining terms don't disappear, then how is this ever going to converge to an actual value? And the proof is a little bit tricky, but you're going to see it again. So I let it go in an effort to just play with these for now, make a few Taylor polynomials, right? And then later we can prove, yes, they really do work, right? It really does converge. So how are we going to check that we got it right? Maybe we graph sine, and then we graph our polynomial, and they should agree, right? They should certainly agree at pi over 3. So let's do that. Share Desmos. Oh, I already set one up for you. I don't want to share this one. I'm going to make a new window. We'll go back to this one. I tried to save a little typing this morning, so I got it preloaded. Okay, so here we go. So you want f of x is sine. F of x is sine. Good grief. Sine x, there it is. And we want to know somewhere near pi over 3. So if you want to put that in there, you can say pi over 3, and then f of pi over 3. So we want them to agree right there, yeah? Don't need this parenthesis. Okay, there we go. So this is the point that we're interested in. So I just stuck it on there. I'm gonna make it red too. Okay, so we want to know, we want an approximation that's centered around here. So we want a polynomial that fits really well right at this point. And we're hoping that that polynomial looks something like p of x. It's gonna start out with square root 3 over 2, oops, 3 over 2. And yep, look at that, it agrees. This green line agrees with our function right at this point. So it's a good approximation, really good approximation right at pi over 3. It fits exactly. But you can see that this keeps going up and this goes down, so it doesn't fit that great for very long. So we try a line. In fact, we tried the tangent line. In fact, this is a throwback all the way back to day 1. So at least a couple of you had to listen to me on day 1. But we wanted to find the tangent line approximation. Remember, find the equation of a tangent line. We talked about that on day 1. And the rest of you, you know, whether that was Janelle or whoever you had. Who did you have, Gloria?
For Calc 1?
Yeah.
I had Kelly Devaney.
You had Devaney. Okay. Well, that you're following in good footsteps there, because her handwriting, her tablet writing is pretty good too.
Yeah, that's where I got it from. Yep. Yep, exactly.
Okay, plus. So what's our slope? Our slope was 1/2, and we had an x. So how come it's missing? And you say, because my polynomial is not centered at 0 anymore, it's centered where? It was centered at pi over 3, right? We moved it over pi over 3. It's been shifted over now. So don't forget that it's not just a straight power series, but it's been it's like a translated power series, if you will. So now it agrees right there. You can see it still agrees right on at this point. And now the green line is pretty close to the red curve for a little bit longer. Well, if a line works good, maybe a quadratic works better. So what do we say? We say plus. I'm going to put the factorials in the front there. And then our term, which was minus square root 3 over 2. And of course, you can put the minus in the front if you want to. And now we have an x minus pi over, minus pi over 3, 3 to the 2nd power. And then I'll just move this over a little bit. And check it out. Now we've got a parabola, and the parabola agrees even longer, right? It's fitting tighter for even longer. So what if we wanted to know the sine of 1 radian? Then we'd say f of 1, right? It's about 0.84147. In other words, the distance up, when I wrap 1 radius around the circle, the distance up is going to be about 0.841. Well, could we approximate that? I don't know. Let's see what P of 1 is. P of 1 looks like 0.84146. So that's pretty good. That's better than the monks, yeah? Do you remember how we did this back in the good old days? You probably heard this story somewhere, but not from me, right? How do we know the value of the sine and the cosine back in the good old days? I'll draw it on the paper off the side here. We hired some monks to make really accurate circles. And then they measured this distance and rolled it up onto here so that the length of this arc and the length of this are the same. In fact, they're both 1. And then they measured this distance up, right? And they measured this distance over. And they called that distance the sine. And they called this distance the cosine. And since it was 1 radian, I'll write cosine of 1. They actually literally just drew an accurate circle and measured it with a ruler. And then, so that they didn't have to do it again, they wrote it down in a book. And people looked up that number in a book for about 1,000 years or so. Well, maybe several hundred years. Until we came up with something better, like maybe like a Taylor polynomial. Yeah? You're remembering this? Okay, beautiful. So I say it's fitting pretty good, but maybe we could make it fit perfectly. I've got P, we'll call this P2, yeah, P2, the second degree polynomial. But I want an infinite polynomial, right? I want the one that fits with all the terms. So let's call that one P of X, and let's say it's equal to the sum n equals 0 to m. I like that n and m. That's working pretty good for me. I think I'm going to stick with that. So how do we get our values? Oh, no, it's going to be hard to put these in here because unfortunately, Desmos can't take the nth derivative. Right? You have to do them one at a time. And so I'm not going to be able to put these in, these coefficients that we're calculating here. Because you can't say f to the n, you know, to get the nth derivative, right? It would be so sweet if Desmos understood that to be the nth derivative, yeah, but it doesn't, okay? So for us, unless we can write a formula for these, okay, I'm thinking that it's going to be hard to expand it because we don't know what our derivative is. In fact, this should be pi over 3. It's the nth derivative at pi over 3. Desmos just can't do nth derivatives, and it doesn't know how to do recursion. So if you want to, you can write them a note that says, you know, it'd be really cool if you guys would do nth derivatives. Okay, so I don't know how to do that in Desmos. Not in terms of a formula. Now we could cheat because this goes root 3 over 2 a half, right? Minus root 3 over 2 minus a half. And then it alternates back and forth. So we could write a really nice piecewise function that had these 4 terms, and then it rotated around depending on the number of the derivative. But I think that's just overkill at this point. And I think that we can see that we've got the right one. Questions about sine at pi over 3? You good? Okay. Well, I'm thinking there was nothing special about the sine here. So you should be able to find a polynomial, Taylor polynomial, that's centered anywhere, right? It could be centered anywhere. The hard part about this, I guess, is that when you stick in this value of a, you generally get something messy. And when you stick in 0, you usually get something nicer. So we usually would just go with the Maclaurin polynomial. Now, because sine converges everywhere, right? This fits so nice right at pi over 3. But what if we just did a regular old Taylor polynomial, right? And we know how to do that too. So what's that? Well, you stick in 0, right? Instead of sticking in pi over 3, you stick in 0. So we get sine of 0, which is 0, yeah? It's right there, degrees at 0. Okay, so I'll call this q of x. So there's q of x equals 0, it agrees. And then you stick in 1. So the cosine of 1 is 1, yeah? So this is 0 over 0 factorial times x to the 0, boring. Okay, now what's the next one? It's 1, right, over 1 factorial times x to the 1. And now we've got our tangent line. And then what's the next one? We stick in 0 and we get minus sine 0, which is 0 over 2 factorial x to the 2. Okay, and that didn't do much. So then we say, what's the next one? We stick in 0, so we get minus the cosine of 0. So now we get minus 1 over, that's messy. How do I do that? 1 over 3 factorial. I wanted it to look like this. There. X to the 3rd power. And now we've got our cubic. Look at how well our cubic fits. In fact, way over here at pi over 3, it's starting to fit pretty good, isn't it? But check this out. Q at pi over 3, okay, at pi over 3 is 0.8. Oh, it's not that good a fit, right? It fits pretty good, but not perfectly yet. So what will we need? More terms, yes? Did I do that right? Oh, these were these were at 1. Okay, so the question is, what was it at pi over 3? Okay, at pi over 3, it's 8660, right? Root 3 over 2. And so what's this one? 855. So we're getting closer, but we need more terms. So do another term. What's the next one? It's got to have a 0 on top, yeah? Okay, so what's the one after that? It's positive 1 over 5 factorial x to the 5th. X to the 5th. And look at now, 866, 866, 29, 86602. So we're getting closer. Now look at the coefficients. These coefficients are so nice that we're not dealing with this root 3 over 2 half, these weird coefficients. So we should be able to write this one in summation notation. I'm going to call this the 5th degree polynomial. And that was q to the 5th. And then let's do the general case. Q of x. It's equal to the sum. N equals 0 to m of, how do we get those coefficients? For sure, we're going to have an x to the n on the back, yeah? Okay, we're going to have a 1 over n factorial, right? Because the n factorial is going to be down here in the bottom. Okay, but then you say, but wait, this one really goes away, right? This is really just 1. Okay, this one we didn't have to type. This whole term goes away, right? And it sort of looks like this when it's cleaned up. It's not just the n powers, but it's the odd powers. So we want to go something like maybe, what is that? 2n minus 1. And down here we want 2n minus 1 factorial. And now all we got to do is get the numerator right. So what's it doing? It starts at 1, then it's minus 1, then it's 1, then it's minus 1. So it's alternating. So what's that look like? That looks like maybe minus, that's not a minus. Where am I? Okay, minus 1, minus 1. Man, 1 year I'll learn to type. Okay, to the nth power. We need to put in an m now. So I'm going to let m start at 0, go out to about 30. Whoops, 0, go out to about maybe 30 by 1s. And what do we got? I'm kind of hoping that, oh, this is a mess. Let's turn off that. Oh, that point can stay. Let's turn off this approximation. Let's turn off this. Well, that was our 5th degree approximation, right? And so now let's make this one a different color so we can see it a little bit better. Here, we'll make it bright orange. Okay, agrees at 0? Uh-oh, that's not good. So what's wrong?
Would it have to do with the -1 to the nth power?
Yeah, that looks bad, doesn't it? This probably should be to the what? N minus 1 power, yeah? But that would be minus 1. That would still work. Most people would think that's weird though, raise it to the -1 power. So maybe most people would say +1 here. That works a little better. That gets our slope going in the right direction. So this is kind of the importance of checking. Okay, so then what do you got? 2, fits good, fits good. Hey, there's our 5th degree one right there. Oops. We'll put q of pi over 3 here, pi over 3. And then we say the 1st degree one, oh, that's not a very good estimate. That's better. That's a lot better. It's 8660, isn't it? And so once we get out here about there, look at that. The ninth one with 9 terms, it fits exactly. Well, it fits to 10 decimal places. How are we doing? Do you have to write it this way? No, but I think that's how we did write it. Did you write it on your list of important ones? The Taylor polynomial for the sine? Let me see what the book wrote. There is a page in your book of ones that you should have memorized. Where is it? There's sine. There's the page of ones you should definitely have memorized. And I'm thinking that not only should you have these memorized, here, let me quit sharing this, stop sharing, so you can see the book. Okay, so not only should you have all those memorized, but you should probably have maybe a couple more. We did a couple more in class, but I would think it would serve you pretty well to know those. Now, of course, I'm giving you kind of a, I'm kind of proctoring, right? So that I'm making sure that you're not working with your neighbor so that my department chair is happy. But more or less, you've got some resources, right, that you can use that you can use during your test. So do you have to have these memorized for this test? No, you can just look them up. But somewhere down the road, it's going to save you a lot of time if you have a memorized, say, for differential equations or Calc 3. So I would say, remember those lists of things that we had you memorize: trig identities, derivatives, antiderivatives, and now series. There isn't much in math that you really have to, multiplication table. There aren't really that many things in math that you really need to have memorized. Okay, unit circle, I'm thinking of a few more. Okay, there's a few things that are coming to mind now. Okay? This should be on your list. So if you've got a little room still in your brain to memorize things, okay, then put this on your list. So what did we do? 1 over 1 minus x. I think Gloria did that one for us. I did e to the x. I don't remember. Either Curtis or Katie did sine and cosine. We did inverse tangent, but we didn't do it using Taylor's method. How did we get inverse tangent? Well, I can't get it to focus. It doesn't like focusing on the book, sorry. How do we get inverse tangent? Where's Shane? Shane usually jumps in right about now.
We did regular tangent, not.
You did regular tangent, but yeah, we did regular tangent the hard way, right? We took the derivative, plugged it in. Okay,
Yeah.
How do we get inverse tangent? Oh my goodness. You guys forgot 2 weeks ago already? We have to have more quizzes more often, huh? Do you remember this? Oops, no, you can't see it. Do you remember this one?
Oh, yeah.
We did this, didn't we? Do you remember that? That's inverse tangent, isn't it? So what was the trick? Write the series for this one, anti-differentiate term by term. But that begs the question, how do you get the series for this? Oh, now you have to remember 2.5 weeks ago. This is all on the test. So you can do a little reviewing.
From what I remember, we just took our first one that we derived, which was 1 over, it was x minus 1 or 1 minus x, and we just changed it using algebra to look like that.
That's exactly what we did. We
Yeah,
found
like
a
that.
series. Good grief, I don't know what's wrong with the focus this morning. Well, there aren't too many more days it has to do this. And if I have to teach all next year, I'll get a better camera. Okay, there it goes. Right? We did 1 over 1 minus x, and then we stuck in a minus x squared. So then we got a series for 1 over 1 plus x squared. Then we anti-differentiated term by term. That's how we got inverse tangent. But then you have to remember that, how do we get this one? We got this one 2 ways. What does this thing mean in the middle? This long bar right here, what does this mean?
Divide.
That means divide. Can't you just take 1 and divide it by 1 minus x? That's one way. That was the hard way, right? That was the hard way to do it, long division. Do you remember the easy way? Okay, maybe this wasn't the easy way, but once you know how to do it, it's certainly the easy way. What kind of a series was that?
Geometric.
Yeah, let me write it down. It's a geometric series. It's this one, isn't it? It's a sweet one. What's special about it? What's special about it is that all the coefficients are 1. So it's easy. That's a geometric series. Okay, so how do we get the sum of a geometric series? First term over 1 minus the ratio. Sorry about the focus, there it goes. So what's the first term? 1, what's the ratio? X, 1 over 1 minus x, it's geometric. That begs one more question. I don't know if I'm gonna ask it, but here it goes. How do we know that the sum of a geometric series is this formula? Do you remember how we got that?
Oh, that was a while ago. Oh my
Now you got to remember like 3 weeks ago or maybe a month ago.
Because
Maybe
originally
3
it
weeks.
was
I
a
have that in my
times,
notes.
it was the first term times 1 minus r to the n all over 1 minus r,
Yes.
which
And then
is
we
what
took
we
the
originally
limit.
had.
So then we said that's the limit, right, as n goes to infinity of the first term times 1 minus r to the n over 1 minus r. And then we took the limit, right? And we said it goes to s as long as r is smaller than 1.
Yeah,
But
then
how
we
do we get this
realized,
formula?
that if r was less than 1 and you multiplied it by itself an infinite number of times, it would become 1. So that becomes 1 minus 1, it becomes nothing.
Close, but you're a little bit off.
I
This
have it right
part,
here.
this part goes to 0 if r is less than 1.
Yeah. Oh, yeah.
Okay? But how do we know it was this formula? I mean, sure, once we get this formula, we can take the limit and that term's going to go to 0. But how do we get that formula in the first place? There was a trick. It's a cool trick that you should remember.
Oh,
Here-
I have it. I just trying to not explain it.
Do you remember how we did this trick? 1 plus 2 plus 3 plus 4 plus 5. This trick up to n. How do we get that formula?
Isn't that just? Why is my brain dying?
I don't know. Think about Gauss. What did he do?
Oh yeah, it was
It was,
n times n plus 1 divided by 2.
yes, that's the right formula, but how do you get it?
He like added them all up twice or something like that. Like I don't know, he did some weird thing.
Forwards and
Yeah.
backwards.
Forwards and
Or
backwards.
yeah.
Kind of sneaky, huh? Okay, so how many of these are there? There's n of them. And what do you get when you add this up? N plus 1. There's n of them. But then when we get this sum, we added it up twice. So we got to divide by 2. Pretty cool trick, huh? You should remember this trick. It's a good trick to remember. Here's the other trick, geometric. Ready? Here you go. Now, instead of it being just to the first powers, right? Like this is 1, 2, 3, 4, 5. This is R, 2 powers now. So this is arithmetic and this is geometric. And here's the trick. Multiply the first one by R. So you get R times, this is the sum that we're looking for. Multiply the whole sum by R. I'm going to shift it over and write R plus R squared plus R cubed plus R to the 4th plus dot, 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 plus R to the n plus R to the n plus 1. Does that make sense? Maybe. It's a little.
Oh, yeah. And then when you subtract that, the only terms you're left with is 1 and r to the n plus 1.
That's right. So now subtract. So I got S minus R times S. I'm running out of room. And then I've got these all canceled, don't they? So I've got 1 minus R to the n plus 1. I factor out an S. I divide by 1 plus R. Or sorry, 1 minus R. And I end up with this. Here, I'll just write it like this. So it's not exactly our formula, but it's pretty close, isn't it? Certainly if R to the n goes to 0, this goes to 0 as well. So it's similar to Gauss's trick. Instead of adding them up forward and backward, we multiply our sum by the ratio and subtract. And we get what's called a collapsing series or a telescoping series. Okay, you should remember this trick. This is good because geometric series are important, and knowing what they sum to, right? Maybe you memorize this, but you should also remember, how did I get that? Which is what we just talked about. And once you've got this, then we know this one. This was our beginning Maclaurin series, right? That was our granddaddy of them all. And then once we know this one, we can get that one by substitution, and then we can get arctan by anti-differentiation. Everybody happy? Okay, that's the review. It's a review day. I'm reviewing. Okay. All right, beautiful. So what do we got? We got, I wish I could just put this on the, I don't know. All right, it's blurry, so be it. E to the x, sine, cosine, inverse tangent. We did the log of 1 plus x. How do we get that one? That one's pretty easy. I think that somebody did that one. I think it might have been Carlos or Kevin. Somebody did this one. They did it the Taylor polynomial way. Take the derivative, plug it in way. But there's a faster way, right? What's the relationship between these two things?
Derivative and antiderivative.
Yeah, same as inverse tangent. So we get the log series by anti-differentiating this series, and we get this series by substituting in a minus x into our original series.
Oh yeah, so then it's just the -1 to the n times x to the n. Then we anti-differentiate that and we get natural log.
There you go. Now, you just did it I built it out of old series way, but we could also find this one the straightforward way, couldn't we? Isn't that just equal to the sum n equals 0 to infinity of the nth derivative of our function at 0 over n factorial times x to the n? In other words, can't we just find these coefficients by taking the derivative and plugging in 0? And the answer is sure we can. We can either find them sort of using this clever method that we did first, or we can just find them directly. So why would you do one and not the other? And the answer is, well, it depends. How nasty is finding the derivative? In this case, it's not too bad, but I think this would be faster. And so we've got two methods for finding the series for natural log. And I think both of them are pretty doable. But for some functions, one's going to be easier than the other. And that might be the method that you end up using. Okay, we got one left on this list. I don't know if you can see it. Here, I'll hold it up. It's that one. It's 1 plus x to the k power. And that's the next thing on my list. So let's get to it. Ready? Here it is. Here's the things we were supposed to do today. You're supposed to do sine at pi over 3. Then you're supposed to do 1 plus x to the k. I'm going to try a different angle. Maybe if it's at a different angle, it'll be better. I don't know what's up with it just doesn't want to focus today. Maybe my iPad needs to be updated. There you go. Okay, so we've got 1 plus x to the k. I'm going to run out of time, like always. So check this out. How do I get this one? Well, isn't that just equal to 4 minus x to the half power? That's looking a lot like 1 plus x to the k, where k is a half. But I don't like this 4. It's supposed to be 1 plus x. So I need to factor a 4 out. Right? So pull out a 4. So how do I pull out a 4? I pull out a 4 out of that by making it x over 4. Am I missing a parenthesis? Missing one parenthesis. Yeah? Factor out a 4. But wait, it's supposed to be plus. So can I put the minus inside and write 4 times 1 plus minus x over 4, right, to the half power. And then wait a minute, this is the square root of 4, so that's just a 2. So if I write it out, I've got 2 times 1 plus the minus x over 4, right, to the half. So let's see. Is that looking a lot like this formula? 1 plus x to the k. This is 2 times 1 plus some value of x to the k, where k is a half. I'm going to argue that if we can do number 2, then with a little algebra here, changing it around, we can get number 3 using our formula for number 2. Is that making sense? Here's the beauty of it. That k in number 2, that k can be any real number. So you could find cube roots or 2/3 roots or raise it to the pi power. The thing you're going to see most often in other math classes as you're going down the road is that k is going to be 1/2, and you're going to deal with a bunch of square roots. Okay, so it's going to allow you to develop series for square roots of things. And so you're going to see k equals 1/2 a lot. But k can be anything in this formula. And so we still have the formula to do. Okay, and then I'm going to do it last. So let's do number 4 next. Are we good with getting 3 from 2 if we can get 2? You're going, yeah, you did that pretty fast. I might have to look at it again myself. But okay, look at it again yourself later. And I think you're good. How do we get 4? Because I can't anti-differentiate e to the minus x squared using any anti-differentiation techniques in the world. And certainly not any we learned from chapter 7. So what do I do? You got to replace that e to the minus x squared with its series, with its Taylor series. In this case, it's Maclaurin series. Do you remember a Maclaurin series for e to the x? This is one you need to have memorized.
X to the n over n factorial.
X to the n over n factorial. So it sounds to me like Shane likes to memorize these in summation notation. I always struggled with that. For me, it was easier to see this as 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed. I always see them in my head when I have them memorized. I always see them expanded. Okay, some people see them expanded. Some people see them more easily in compact summation notation. You certainly should be able to change between these, but I don't know how your brain's going to memorize them the best. So you might memorize them in this form, or you could memorize them in this form, or maybe you just memorize them in both. I don't know. But it seems to me like even though Shane remembered it this way, that if I'm going to anti-differentiate term by term, I'm eventually going to have to put in all these terms so I can do them term by term. However, we know that the integral of the sum is the sum of the integral as long as that works, which we didn't prove yet, some graduate class down the road, which means I can put the integral inside here, and then I can just anti-differentiate this formula. So whether you do it term by term or just do the formula directly is kind of a matter of preference. Okay, since Shane started us off, I'm gonna keep going in his direction. I'm gonna say the integral now of the sum of x to the n over n factorial dx. So everywhere I see an e to the minus x squared, I put that, and then of course I'd be wrong because this is the formula for what? That's e to the x. And what do we really want? X is an x. X is?
Negative x squared.
Yeah, negative x squared. So maybe what I really need is negative x squared to the nth. Feeling better? Yeah, me too. Okay, so now we do what? Now we say that's the sum, right? That's the sum of the integral. But what do we do with this definite integral? Like, when do we plug in? Okay, that's a very good question. Right? And what are we plugging in for anyway? What's going from 0 to 1? I mean, we've got a lot of variables running around here, so we might want to label it. What goes from 0 to 1?
Your x value?
X does, right on. X equals 0 to x equals 1. Okay, of what? I'm going to clean this up a little bit. I'm going to write it as minus 1 to the n, x to the 2n over n factorial, yeah, dx. It's a little sloppy. I think we pretty much got it. Okay, anti-differentiate. Oh boy. I'm thinking term by term might have been easier, but here we go. It's x to the 2n now. It must have been what?
X to the 3n.
Oh, close. Not n
Over
times
3.
bigger, but only how much bigger with the power rule?
You add 1 to the exponent?
Just add one. Yeah, not add one n.
Oh, yeah.
Just add a single one.
Oh, yeah.
Okay, so this is our guess. So now I have to take the derivative of this guess, right? And see if I'm right. But of course, I'd still have to have a leading coefficient on here. So this leading coefficient is still the same. N's just a constant. Okay, n's not an x. So this stays here. But then when I take the derivative, right, I'm going to have to get rid of this 2n plus 1.
So 1 over 2n plus 1.
So I think I need a 1 over 2n plus 1 in there as well. X to the 2n plus 1. And now I'm worried about one more thing. I'm worried about, where does the index start? Because I know when I take the derivative, it's going to start at 1. But when I take the antiderivative, does it start at minus 1? I'm worried about the index here. So I either have to remember what the rule is, okay, look back in the book and see what the rule is, try this, put it on Desmos and check it out, test it, right? That would work. Or maybe I just do it term by term, and then it just starts where it starts, and I don't have to remember what the index is. And since I have trouble remembering the index, I would be more inclined to do it term by term, and then it just starts where it starts, and then I don't have to worry about it. Are you with me? I'm saying that we might have a problem right here. I don't know if that's right or not. How are we doing?
Because, well, I mean, you would be starting one term ahead.
Right, so does n start at minus 1? And if it does this have to change? If you want to start at 0, should this really be an n plus 1 factorial? And this be an n plus 1, and this be an n plus 1? Should all the n's be 1 bigger? Seems like that seems about right to me.
Yeah, that's what I was thinking.
Okay. We probably would not say that n starts at minus 1, yeah? That would probably not be good. You should either start at 0 or 1. I'm guessing that WebAssign's not going to take it if you say start at minus 1. So you're going to have to fix the index. But I don't know how to fix it, and I didn't do enough of these that I have it memorized. So I would end up having to check this using Desmos anyway. Okay, or go look in the book, or go type it into Symbolab. So for me personally, okay, I know there's something going on here. I know there's something with the index going on here. I don't know what it is, and I don't want to waste my brain power of trying to figure it out. So I just type this into Symbolab and see what the answer is. Let Symbolab remember for me, or let Wolfram Alpha remember for me. Okay, because I got a lot of other things I'm supposed to remember. But should we be able to figure it out if Wolfram Alpha is broken? Sure. Okay, but it might take going to Desmos to figure it out. In the meantime, let me look at the alternative. The alternative was, let's do the integral, okay, of our sequence. So I'm going to stick the x minus x squared into our series. Okay. Yeah, just stuck minus x squared into our series for e to the x. And now I can just go term by term. So what do I get? Maybe I want to clean this up one more time before I do that, because I might make a little mistake there. Don't want to lose any minus signs. So I'm going to say minus x squared plus 1/2. Because the minus is squared, it's positive, x to the 4th. Then it's going to be minus 1/3 factorial x to the 6th plus, right, 1/4 factorial x to the 8th, okay, minus ... and a dx. How am I doing so far? Still good? I'm not feeling good. Are these bottom numbers right? They look right. Yeah, they look right. Okay, do it term by term. X minus 1/3 x cubed, right? Plus, what is this? This times this, 2x to the 5th, yeah? Plus what? This is a 6, and it's a minus. So this is minus x to the, oops, I messed it up. This goes to the 5th. Maybe I should write it like this. Just leave the half right there for now and put the 1/5, right? X to the 5th right here, because then it'd be easier to see the pattern. And then go minus 1/3 factorial, and then we get 1/7 x to the 7th, right? And then keep going. And then what's left? Stick in 0 and 1, yeah? This is nice because sticking in 0 is easy. So sticking in 1, we get 1 minus 1/3 plus 1/10 minus, what is that? 1/3 factorial times 7. So then it would be plus 1/4 factorial times 9. How are we doing? Still good? How can we check? I mean, this was a whole bunch of math going by really fast, so I don't know if we got this even close to right, right? We might have to, I mean, I think we thought about it right, but I'm not sure if the details are right. So what I would do is I would go over to Desmos. I would maybe start with a new one, and then I'd probably put this in, and I'd say, what do I want? I want the integral from 0 to 1 of e to the minus x squared, right? Dx. So I'm supposed to be getting this. And what is that? Well, maybe I just do this instead. Copy f of x. And then I come down here and I say f of x is this, so that I can look at it, right? Here's a nice picture of it now. So what do we really have? We got the area under this little half of this arch that goes out to here, this little wedge right here. So the area of this box from -1 to 1, well, that's 1. So this says it's about 3/4. Well, right here would be half. So if I go kind of angle it down like that, does that look like it could be 3/4 to you inside here? Looks pretty reasonable. So how did Desmos get this number? That's my question to you. And I say there's 2 ways. It's review time again.
Either it did this, what we're doing right now, and it did the series,
You could do the series, you sure could. But wasn't there an easier way?
Make a bunch of boxes.
Make a bunch of rectangles, right on. Can't you just put a bunch of rectangles here and add up all the rectangles from 0 to 1?
Yeah.
Take the limit as n goes to infinity, the limit of a Riemann sum. Oh yeah, I remember Riemann sums. Here's some good news for you. Ready? I hate to even say this out loud. There are no Riemann sums where you have to do that big 5-step process on the final. Okay, but there could be some Riemann sum, questions about Riemann sums. But you remember that big long thing where we had to say, what's delta x and what's x, what's a plus b, a plus I delta x, and then substitute it in and do the Riemann sum and take the limit. Oh, God, that was terrible. Remember that? Just nod, okay? Otherwise, you might tempt me to put it on the final. There will be some things about Riemann sums. For sure, we should know what a sum is, and we should know that if we want an area, we want to add up a bunch of rectangles. But there isn't one of those big page-long computations that you have to do on the final exam. Okay, so I think that was like quiz 5-1 or something like that. It's right at the beginning of this class, which probably seems like 100 years ago. Okay, so how could we do it now? If you don't like Riemann sums, how could we do it now? Couldn't we just model this function using a Taylor polynomial? And if we did it right, isn't our Taylor polynomial something like 1 minus 1/3, oops, no, the polynomial, before we anti-differentiate it, 1 minus x squared plus, good grief, get over there, whoops, whoops, why is it doing this to me? Back up. 1 plus, this should be x squared, and then we got plus 1/2 x to the 4th. Hey, this looks like we got the right one now, doesn't it? It's starting to fit pretty good. So then we've got what? 1 over, oops, whoops, 1/2 x to the 4th, yeah, minus 1/3 factorial x to the 6th. Still fitting pretty good? Go over a little more. 1, good grief, why is it doing that? Plus, okay, 1 over, what's the next one? 4 factorial x to the 8th. Check it out. I'm going to make it a little smaller. Check it out. Would you say that the area under the green thing from 0 over to 1 is pretty close to the area under the blue thing? I mean, that looks pretty good. If I can find the area under this, I should be able to find the area under the blue thing, because the green thing's starting to look a lot like the blue thing. Now, what's the problem? Well, the green only fits the blue between -1 and 1. So right in here, it's starting to fit not so good, right? So we would have to maybe put some more terms on so that this thing, fits better and better and better. Because right in there, although they coincide, right? One's sitting right on top of the other. It's starting to look like it might be moving apart from each other. So maybe I put a few more terms on. So now what do you do? Well, now you could certainly do this, the integral from 0 to 1 of p of x dx. And so check it out. It's pretty close, isn't it? 747, 746, they're almost the same. So why aren't they the same? Well, I only did 5 terms here. So I would need more terms. And the more terms I make, the closer these are going to get to one another. How are we doing? Good? I don't know for sure that you're going to need to look at the pictures. Okay, what I find is that sort of graduate level math types sort of wean themselves off of using a concrete picture. It turns out that when you get to Calc 3 and you're working in 3D, there's not a really nice kind of 3D Desmos that makes nice 3D pictures. And then, hey, guess what? When you get beyond Calc 3 and you want to do more dimensions than 3 dimensions, like you want to do 4th dimension, now it's going to be really hard to graph. And so what we find is that using the graph to kind of check your understanding, it's at its highest point right now. Okay, you can really use Desmos to help check your understanding right now. But when you move to 3 dimensions, it's harder to use the graph because it's harder to make the graph. And then when you move to 4, 5, 6, 7, 8, 10 dimensions, then we can't even make a graph anymore. And so this idea that we can use the graph to check, you should live it up because it's going to go away. And then we would have to use algebraic or alternative methods for checking, or maybe you know, you do this in one room and someone does it in the other room, and if you two get the same answer, then we feel like it might be the same answer, the right answer. Okay, so using the graph as justification is kind of going to go by the wayside as we get, say, 3 or 4 more classes down the road. But you can certainly use it right now, and I think that it really helps to confirm that the way you're thinking about it is the right way. Okay, so I would definitely use Desmos as much as I could. And if you had me for Calc 3, some of you will be pretty thankful that you aren't going to, right? Because I don't teach at Calc 3 in the fall, so too bad. You got to take somebody else, right? But that's probably about time for some of you anyway to move on. You know, I like looking at it. I do a lot of 3D graphing in my Calc 3 class. And so, but you already had an introduction. So you can use CalcPlot 3D, kind of take the place of Desmos as you move down the road. And depending on who you get, maybe they'll do a lot of graphing, maybe they won't do so much, right? But for now, I would definitely use Desmos. If you want to use Desmos to justify an answer on your final exam, then you can just put it in there just like this, and then go screenshot and paste it into your document. That works. And then you can say, I did it on Desmos, here it is. And it only takes like 2 seconds to screenshot it and drag it into your justification document that you're gonna upload on the last question. So you can certainly do that, okay? Questions about that? All right, I'm feeling like we got this. So we got one thing left. Oh boy, and we're really, really out of time. You know what? I think I'm gonna save it. I'm gonna save it. I was trying to get this done. I was trying to get this done today, but I think it's maybe best to just save it. This will be our last hurrah, okay? So Friday, I wanna do this one. And then I want to answer any questions that you have about chapter 11 so that you can do the second half quiz. Second half quiz is just on Taylor series like we've been working on. And then I want to answer any questions that you have about the final exam, right? Or the ones that you can think about by Friday. So we'll do half the time talking about the binomial series. And then we'll spend the other half answering your questions. And then that'll be it for Friday. Does that sound okay? I think we got enough for one day. All right, so you keep working on the homework. I think I mentioned to you already that the homework is going to be due on the night before the test. So Tuesday night at midnight, okay, is when I left it all open for you in case you wanted to do some more studying. I will be in and out, okay, for all the rest of the days until you take your final. And so you can catch me at office hours online, or you can write me an email and I'll write you back. Any of that will work if you think of some things between now and then. Katie, what do you got?
So just to clarify, Friday their last class day, and then we're meeting again for finals on Wednesday.
That's correct. And we're going to meet
Same
at
time.
8 o'clock. Yeah, earlier. 8 o'clock. I'm going to open it up from 8 to 12 so that you have lots of time.
Okay.
Okay, if you want to show up sleep in a little bit, show up at 9, you still got 9 to 12, that's still fine. Just, just check into the Zoom, say that you're ready to go, and then you can get started on it.
Okay.
Other questions? How about you guys? Boaz, Carlos, Curtis, any of you guys have, oh, Curtis is on there. Shane, any of you guys that are just on the chat, any questions from you guys?
I have one question, but it's not really related to the stuff we've been talking about.
Okay.
It's from the homework on 11.9.
11.9 homework. Okay.
Yeah, way far away.
All right.
But it's more a question about the formatting of the question.
Okay.
It's just like a free response kind of thing.
All right.
Oh, yeah.
And I've got like the overall idea of it. I'm just not
Okay.
sure how to input it.
Okay. Tell me what the question
Because
is.
it's asking, basically asking about recursive.
Do you remember the number?
Sorry, I think I might have a bad connection.
Do you remember the
It was 12, I believe.
Well.
Yeah. This is the one that me and you worked on in the
Uh-oh.
office hours.
Oh, it is?
Yeah, number 12. I remember this one. It was just a box to fill out.
Yeah, and so I feel like the answer to the
Can't plug
question
it.
is a mathematical expression, but I'm not
Okay.
sure how to input that in if it's just a text box. Am I just
Oh.
supposed to explain it in words?
I
That's
don't
kind of
know.
what I did.
What did you do, Katie?
I just explained it in words, like instead of being able to actually type like an actual sum, I just said the sum from this to this, and I think it gives you credit no matter what you say in the box. But I mean,
Okay.
Okay, try that. And then I will
Yeah.
go
Yeah,
look.
no,
at
I
it. You
just
said it's
wanted
number
to.
12, right? 11.9, number 12. Okay,
Yep.
I'll go look at it in WebAssign and see if I can
Yeah.
figure out what else. But yeah, just try typing something in the box and see if it gives you credit for it.
yeah,
Okay.
I just typed kind of the word format of what like
Yeah.
the equations were, and then just
Okay.
good.
It's really hard sometimes for WebAssign to do open-ended type questions, right? And so it probably intended for me to go back there and look at your work and give you some feedback. And I didn't get that far. So if the problem is not making sense, then we should talk about it. But if you just need to type something in the box, then just type something in the box and move on. Does that help?
Oh, I think he's connection.
Yeah, and you might have.
Okay.
Yeah, you're
Yeah.
in and out a little bit. Okay, good. All right, and I'll go look at it too and see if there is anything else interesting about that one. Any other questions? All right, then. Have a good couple of days, and I will see you guys on Friday for our very last day. All right, take care.
All right. See you then.